Hello and welcome once again to this online session in the subject of signals and systems. Currently we are discussing Z transform as a part of transform domain representation of signals and systems. In last few online sessions we had seen Z transform of some common signals. Let us try to review this Z transform pair. We had used both the approaches for calculating Z transform, namely using the formula for Z transform as well as using the properties of Z transform. And during the discussion we identified that if we have Z transform pairs handy, then using the properties of Z transform it would be very convenient to calculate Z transform of other signals. In line with this, let us try to discuss few more examples of calculating Z transform for different discrete time signals in this online session. Let us start with a signal x of n is equal to 1 by 2 raised to power n u of n minus 1. Right. This signal primarily reminds us of a standard Z transform pair like a raised to power n un equal to 1 upon 1 minus az inverse. Further, because we have u of n minus 1 here, which shows the time shifting of a unit step signal, we also get reminded about a standard property of Z transform, which is the time shifting property. As per this property, if x of n is having Z transform x of z, then x of n minus k would have Z transform z raised to power minus k x of z. It means that x of z would be multiplied by the term z raised to power minus k, where my shift is of minus k. ROC would primarily remain same except z equal to 0 or z equal to infinity removed from the ROC depending upon the multiplying factor z raised to power minus k. So now, if we try to, in light of both the things that we have discussed here, if we have some term like 1 by 2 raised to power n u of n, then we understand from this standard Z transform pair, we understand that its Z transform would be 1 upon 1 minus 1 by 2 Z inverse with mod z greater than 1 by 2. Now, with this as a reference, let us try to see Z transform of a signal 1 by 2 raised to power n minus 1 u of n minus 1. If you try to compare this signal and this signal, what is the exact difference? The difference is that instead of n, which is there here as 1 by 2 raised to power n u of n, we have n minus 1 in both the cases. So simply n is replaced by n minus 1. So we use the time shifting property which says that if you have x of n having Z transform x of z, then x of n minus 1 would have Z transform z raised to power minus 1 x of z. So we try to write Z transform of this as z raised to power minus 1, this term written as it is. Yes? As mod z is greater than 1 by 2, it does not include 0 and hence there would not be any change in ROC. Right? However, we identify that our x of n which is given is not in this form. What is the difference? We have u of n minus 1 coming here, but we don't have 1 by 2 raised to power n minus 1. In fact, we have 1 by 2 raised to power n. Now, this is not difficult to address, as x of n can be written as 1 by 2 into 1 by 2 raised to power n minus 1 u of n minus 1. Because we understand that if we multiply this 2, we would ultimately get 1 by 2 raised to power n. So now, x of n can basically be represented as 1 by 2 into this. 1 by 2 being a constant, if I take a Z transform, I can actually write this Z transform multiplied by 1 by 2. So, Z transform of x of z becomes 1 by 2 Z inverse upon 1 minus 1 by 2 Z inverse mod z greater than 1 by 2. Yes? Let us try to take one more example in this regard. X of n is equal to minus 1 by 2 raised to power n u n convolution 4 raised to power n u of minus n. So the discrete time signal that is given to us is primarily convolution of two signals. So here x of n, I try to represent it as x1n convolution x2n, where x1n is this particular signal, whereas x2n is 4 raised to power n u of minus n. Now as per convolution property, we know that convolution in time domain is basically multiplication in z domain with the net ROC as intersection of the two individual ROCs. So if I want to find z transform of x of z, I can individually find z transform of x1n and x2n, and then I can multiply two z transform so as to get the overall z transform. So let us try to consider the first case, minus 1 by 2 raised to power n u of n. Now this term is exactly in our standard form a raised to power n u of n, whose z transform is 1 upon 1 minus a z inverse mod z greater than mod a. The value of a is, in this case, is minus 1 by 2. So if I try to find x1z, then x1z would be 1 upon 1 minus of 1 by 2 z inverse mod z greater than mod minus 1 by 2, which is nothing but 1 upon 1 plus 1 by 2 z inverse mod z greater than 1 by 2. Similarly, if we try to see x2n, then x2n is 4 raised to power n u of minus n. To bring it in the symmetry of minus n, keeping the variable minus n to be same in both the cases, we understand here you have plus n, here you have minus n. To make this also minus n so that it comes in a symmetry, I write it as 1 by 4 raised to power minus n u of minus n. Now this reminds us of a time reversal property. A time reversal property says that if x of n has z transform x of z, then x of minus n would have z transform x of z inverse, and ROC would also get inverted. So now, if we know that z transform of a raised to power n un is 1 upon 1 minus a z inverse, then this is nothing but a raised to power minus n u of minus n, that is, z transform of x2n can be taken by replacing this z by z inverse. That is, if we have 1 by 4 raised to power n u of n, then this would give me z transform 1 upon 1 minus 1 by 4 z inverse with mod z greater than 1 by 4. x2 is basically x2 is basically time reversed version of this signal. So z transform of x2z can be calculated simply by substituting this z by z inverse. So we have 1 upon 1 by 4 z inverse raised to power inverse. So this remains as it is. This z is also replaced by z inverse. If I try to simplify this, this would give me 1 upon 1 minus 1 by 4 z mod z less than 4. So now we have got z transform of x1z, we have got z transform of x2z, which are given here. We want to find z transform of x of n, so we would primarily say z transform of x of n, that is x of z, would be multiplication of these two, that is 1 upon 1 plus 1 by 2 z inverse multiplied by 1 upon 1 minus 1 by 4 z. The ROCs of the two are mod z greater than 1 by 2 and mod z less than 4. So the first ROC is mod z greater than 1 by 2, so it is outside this inner circle. And the second ROC is mod z less than 4, which means that it is inside this inner circle. So if inside this outer circle. Mod z greater than 1 by 2 is outside this inner circle, and mod z less than 4 is inside this outer circle. And hence, if you try to find the common area would be 1 by 2 less than mod z less than 4. If we want to simplify, we can simplify this expression here by taking LCM. This would basically give us some expression like this. So, even though we have convolution of two signals, it is very easy to calculate its Z transform if we try to look, or if we try to decompose the given signal in terms of the individual components, and if we try to take reference of few properties of Z transform as well as standard Z transform pair. If required, you can take a pause here, you can go through the example once again, and I am sure you would not find it difficult to understand. If we are through with this, let us try to take one more example in this regards. Let us say we have something like x of n is equal to a raised to power minus mod n for all n, given that mod a is greater than 1. Understand that x of n is primarily a non-causal signal because it spreads on both sides of n equal to 0. Now because we have this mode, we can actually write x of n as summation of or combination of two signals as follows. X of n can be written as a raised to power n for n less than 0, and it can be written as a raised to power minus n for n greater than or equal to 0. In fact, we have discussed this concept before also. Let us try to revise this. What is the importance of this mode here? We know that n primarily belongs to Z. So n can be negative as well as n can be positive. However, n would be an integer. Putting this mode here would assure that the value of n, whether negative or positive, would ultimately result into a positive value. That is, this minus sign which is in the power of a would remain as it is. So, if n is negative, for example minus 2, then mode of minus 2 would basically give you 2. So, it would be a raised to power minus 2. Now, if I remove mode and n is negative, and then I can simply write it as a raised to power n, because if n is minus 2, this would give me a raised to power minus 2. Similarly, if a is greater than 0, if a is positive, then in any case the mode is not required. However, the minus sign should stay. So now I write it as a raised to power minus n. That is, say for example, if your n is equal to 2, then you would get a raised to power minus 2. Put n equal to 2 here, you would get a raised to power minus 2. So this is how we can remove this mode, and we can bring it in the form that we are generally aware of or generally we use. Right? Now, further, if we try to see, x of n is equal to a raised to power n for n less than 0, that is from minus infinity to minus 1. So I can write x of n as a raised to power n u of minus n minus 1, because u of minus n minus 1 is equal to 1 from minus infinity to minus 1. And the second term, I can write it as a raised to power minus n un. Why? Because un is equal to 1 for n greater than or equal to 0. So, I can express this x of n as summation of two signals. One is pure anti-causal signal, another is pure causal signal. And now you can understand why we are interested in doing this, because this represents some standard signals for which we have a standard Z transform pair. So let us try to recollect this. We know that minus a raised to power n u of minus n minus 1 has Z transform 1 upon 1 minus a Z inverse. Being anti-causal, the ROC is mod Z less than mod A. Similarly, if we have a raised to power n u of n, then its Z transform is 1 upon 1 minus a Z inverse. In this case, mod Z greater than mod A. So now, if we try to see x of n, and if we try to express x of n as given here, then we will be able to match to the standard form. That is, the first term, we know we need a minus sign here, so I bring a minus sign and I put a minus sign outside the bracket, so minus minus becomes plus, so I would actually not changing the term. However, I am trying to represent it in the standard form. So this is minus a raised to power n u of minus n minus 1, another minus sign outside, plus I want it in terms of a raised to power n u of n, so I write this a raised to power minus n as 1 by a raised to power n. So now, using the standard Z transform pair, we can write x of z as, this minus comes as it is, Z transform of this is 1 upon 1 minus a z inverse. Z transform of the second term would be 1 upon 1 minus 1 by a z inverse. And the ROC of the first term, is mod z less than mod a. ROC of the second term is mod z greater than 1 by a. Yes. So if we the value of a, you would understand this, the value of a here becomes very critical. Let us try to take two cases. The first case, the case given here is mod z greater than 1. So let us take the value of a to be equal to 2. So the ROC says that mod z should be less than 2 and mod z should be greater than 1 by 2, that is 0.5. Now this makes sense because ROC then can be between 0.5 and 2, because ROC should be greater than 0.5 and less than 2. So we have a common area in between, which is the area between z equal to 0.5 and z equal to 2. However, if this a is less than 1, say for example 0.5, then this says that mod z should be less than 0.5, and this says that mod z should be greater than 1 upon 0.5, that is 2. So here there is no common region between the two, because this says less than 0.5 and this says greater than 2, so there is no common region. However, in this example specifically, we are saying that mod a is greater than 1, and hence we can write the common ROC as 1 by a less than mod z less than mod a. Yes. However, if it would have been a case like mod a is less than 1, then we would say that there is no common region in ROC, and hence Z transform does not exist. Fine. Having done this, let us try to move on to the next example, where we try to investigate the properties of initial value and final value theorem. The question says that find initial and final value of a signal x of n whose z transform is given as x of z is equal to 2 upon z square plus 1 by 6z plus 1 by 6. So what is given to us is z transform of a signal x of n, and what is asked to us is to find its initial value, that is x of 0, and final value, that is x of infinity. Let us try to address this question. We know, as per initial value theorem, the initial value of a signal x of n, that is x of 0, in z transform is expressed as limit z tends to infinity x of z. So I would have to take limit z tends to infinity, I would substitute this x of z that is given to us. Yes. To put the limits, let us try to represent this in terms of 1 upon z, that is in the negative powers of z, so that putting z tends to infinity would primarily make that term to be 0. So I rearrange the terms by taking z raised to power 2 out from the denominator. This would give me 1 plus 1 by 2 z inverse plus 1 by 2 z raised to power minus 2. In the numerator also I would get z raised to power minus 2. Now if I put limit z tends to 0, z tends to infinity, this term would become 0, this term would become 0, this term would become 0. So primarily you would have 0 by 1, which is nothing but 0. So the initial value of the discrete time signal x of n is 0. Similarly, as per final value theorem, what we have? We have x of infinity equal to limit mod z tends to 1, 1 minus z inverse x of z. Yes. So, substituting the values of x of z, which is nothing but 2 upon z square plus 1 by 6z plus 1 by 6, with this multiplying bracket 1 minus z inverse. Right? We find that if we substitute the value of z to be equal to 1, this term basically becomes equal to 0. Right? Whereas in the denominator I am left with 1 by 6. However, 0 divided by 1 by 6 is nothing but 0. So here we use initial value theorem and final value theorem to calculate initial and final value of a signal x of n. With this, we end this online session, and in the next online session we would start with inverse Z transform. I would request you to go through your text and try to solve as many examples as possible for calculating Z transform. As you solve more examples, you would become more familiar with standard Z transform pair and properties of Z transform, and you would find that with more practice this becomes more and more easier. Thank you for joining this session. Thank you very much.